Hello friends, today we are going to cover network theory topic transient. Transient is basically of two types. One is DC transient, another is AC transient depending on the sources present in the circuit. First we will go ahead with DC transient. Consider the basic elements of network theory, that is R, L and C, that is resistor, inductor and capacitor. Consider the case of resistor first. Let's say VR is the voltage across resistor and IR is the current passing through resistor. Then using Ohm's law, VR is equal to IR multiplied by R. So IR is equal to VR upon R. That means at any time instant t, current through resistance depend on the voltage across resistance at that time instant t only. That means it is one-to-one correspondence. That means resistor does not store any information in it. So it's a memoryless element. Consider the case of inductor. Let's say VLT is the voltage across inductor and ILT is the current passing through inductor. Then VLT is equal to L dit by dt. Rearranging the same for ILT, we get 1 by L integral VLT dt. That means current through inductor at any instant t depends not only on the present value of voltage across inductor, but it also depends on the history of the voltage values. So since history comes into picture, it is an element with memory. Similarly, consider the case of capacitor. Let's say VCT is the voltage across capacitor and ICT is the current passing through capacitor. Then ICT is equal to C dVc by dt. Rearranging the same for voltage, we know VCT is equal to 1 by C integral ICT dt. Now, voltage across capacitor at any instant t depends not only on the present value of capacitor current but also on the history of the capacitor current. That means it is also an element with memory. Now, if network consists of only resistors, that means resistor does not store any energy, so it allows sudden changes in the energy of the circuit. Whereas in case of inductor and capacitor, since these are energy storing elements, these opposes sudden changes in the energy of the network, which causes transient effect in the network. Transient is nothing but oscillation effect in the response of the circuit. Now in case of inductor, if L is the inductance value, I is the current passing through it, then magnetic field will get generated around inductor, and that is given by magnetic flux is given as psi is equal to Li. So energy is stored in the form of magnetic flux in inductor. Similarly, in case of capacitor, let's say V0 is the voltage across capacitor and capacitor's value is C, then charge stored on capacitor is given by CV0. So energy is stored in capacitor in the form of electric charge. Now this charge is stored in the form of voltage, right, V0, and in case of inductor it is current, that is I0. Now because of the energy storing properties of these two elements opposes sudden changes in the energy across these elements. So inductor stores in the form of current, capacitor stores in the form of voltage. Hence inductor opposes sudden changes in the current passing through it, and capacitor opposes sudden changes in voltage across it. Now consider the case of RC circuit first. Let's say voltage is applied across RC circuit which changes from 0 to Vs value at t is equal to 0. So for time instant t less than 0, current through RC circuit will be 0. But at t is equal to 0, voltage Vs will be applied across RC circuit. And let's say IT is the current flowing through it. Now from time t is equal to 0 to time t is equal to infinity, this voltage source is applied across RC circuit. Whenever source is applied to RC or RL energy storing elements at t is equal to infinity, that means after a very long time the circuit reaches in steady state. Now what does it mean by steady state? That means energy stored in the circuit is maximum and constant. Now since this is RC circuit, energy is stored only in capacitor because resistor does not store any energy. So at t is equal to infinity, capacitor energy will be maximum and constant. Now current through capacitor is given as C dVc by dt. But what is Vc? Vc is going to be maximum and constant since energy stored in capacitor in the form of V0, that means voltage. So C dVc by dt will give you 0 value. That means capacitor current at time t is equal to infinity is 0, that means in steady state. Capacitor current is 0, that means capacitor acts as open circuit in steady state condition. Similarly, consider the case of RL circuit. Vs is applied, voltage source is applied across RL network and at t is equal to 0, the voltage value, input value changes from 0 to Vs. Now since we are going to apply this voltage Vs from t is equal to 0 to infinity, that means for a long time, after a very long time, energy of circuit will be maximum and constant, that means in steady state condition. In case of inductor, energy is stored in the form of current, that is I0. So energy of inductor is given as half Li square, but I is nothing but maximum and constant in steady state, that means it reaches at the saturation value of energy storing capacity. So IL will be maximum constant. So what is the value of VL is equal to L dIL by dt, but IL is maximum constant. So what is the value of VLT that we get at t is equal to infinity, that means in steady state, that is equal to 0. That means voltage across inductor is 0, that means inductor acts as short circuit in steady state condition. Now we will see response of the L and C elements at switching instant. Let's say voltage is applied which changes from 0 to Vs at t is equal to 0. Now also consider one case on time scale at t is equal to 0. We are going to consider two instances, that is at t is equal to 0 minus, that means just before time t is equal to 0, and t is equal to 0 plus, that is just after t is equal to 0. So this time duration is infinitesimally small. Now we have already seen that capacitor opposes sudden changes in the voltage across it and inductor opposes sudden changes in the current through it. So Vc at 0 minus will be equal to Vc at 0 plus, because capacitor won't allow sudden changes in the voltage across it, and similarly IL at 0 minus will be equal to IL at 0 plus. That means inductor won't allow sudden changes in the current across it. Now consider the case of capacitor first, RC circuit first. Then voltage changes from 0 to Vs value. What will be the condition at t is equal to 0 minus? At t is equal to 0 minus, since Vs is 0, what is the voltage across capacitor? That is nothing but 0, because capacitor is initially discharged, right? So at t is equal to 0 minus, capacitor Vc is equal to 0, and as we have seen that Vc 0 minus is equal to Vc 0 plus, so Vc 0 plus is equal to 0. Now we'll redraw the circuit at t is equal to 0 plus. Right? But what is the Vc 0 plus? Voltage across capacitor at 0 plus time? It is nothing but 0. That means at t is equal to 0 plus, capacitor acts as short circuit. So capacitor acts as short circuit at switching instant. Now consider the case of RL circuit. As we have seen, IL 0 plus will be equal to IL 0 minus. Now consider that initially inductor is discharged. So at t is equal to 0 minus, Vs value is 0. So current through circuit will be 0, right? That means IL at 0 minus will be equal to 0. Now at t is equal to 0 plus, as we have seen that inductor value will be same as inductor value at t is equal to 0 minus, that means it is nothing but equal to 0. Inductor current equal to 0, that means what? Inductor will act as open circuit. At t is equal to 0 plus. That means inductor acts as open circuit at switching instant. Now we are saying that at switching instant, that means instead of applying a step input, we can also represent it in the form of a switch. That means this switch will be closed at t is equal to 0, let's say. That means what? Up to t is equal to 0, Vs is equal to 0 because Vs won't be applied, and after t is equal to 0, Vs is equal to Vs value, that is plus positive Vs value, right? According to the step input. So instead of applying a step input, we can also represent in the form of switch. That's why I am saying that capacitor will act as short circuit at switching instant. That means when Vs is applied from 0 to Vs value and voltage source is applied from 0 to Vs value, and inductor acts as open circuit at switching instant. So till now we have seen that in steady state, capacitor acts as open circuit, inductor acts as short circuit. At switching instant, capacitor acts as short circuit and inductor acts as open circuit. Now we have seen the switching instant condition when L and C were initially discharged. So now we will see equivalent L and C circuit with initial conditions. That means L with initial current I0 and capacitor with initial voltage V0. Let's say RC circuit with initial voltage V0, and at t is equal to 0 switch will be closed. Let's say Vs is the voltage source applied. Then equivalent of this has to be represented. We have already seen that at switching instant capacitor acts as short circuit. Switch is closed at t is equal to 0 plus. Let's say these are A and B nodes. So voltage across capacitor has to be same at t is equal to 0 minus as well as t is equal to 0 plus. That means Vc at t is equal to 0 minus is equal to Vc at 0 plus, that is equal to V0, right? Now at t is equal to 0 plus, as we have seen that at switching instant capacitor acts as short circuit. So let's say capacitor is short circuited. But what about V0? It has to be there between the nodes A and B. That means it comes in series with the short circuited capacitor with the given polarity plus minus V0. Now consider the case of RL circuit. Let's say with initial conditions I0 and switch is closed at t is equal to 0. We know that IL at 0 plus will be equal to IL at 0 minus, that is equal to I0, since it is present with initial conditions I0. So at t is equal to 0 plus, let's say switch is closed, and let's say these are two A and B nodes. Now inductor acts as open circuit at switching instant. So inductor will be open, but it has to carry the same current just before switching instant, same as just before switching instant. So I0 has to be there in parallel with the open circuited capacitor. This is the equivalent of L and C elements with initial conditions. Now we'll see few points that are very important from numerical point of view. That one is at switching instant and in steady state, circuit has to be resistive, completely resistive. In steady state, capacitor acts as open circuit, inductor acts as short circuit. At switching instant, capacitor acts as short circuit and inductor acts as open circuit. Now we will see the response of RC and RL circuits. Let's say, now we will see the case of RC circuit with source. Let's say voltage V is applied across RC and C is initially discharged and switch is closed at t is equal to 0. Now for t greater than 0, switch will be closed and circuit will be and let's say IT is the current flowing through the circuit. Then using KVL we can write plus V minus IR minus 1 by C integral I dt is equal to 0. Differentiate it with respect to t, we will get 0 minus R di by dt minus 1 by Ci is equal to 0. Rearranging the same, we get di by dt plus 1 by Rc I is equal to 0. This is nothing but standard first order differential equation. Now its solution is given as it is equal to complementary function plus particular integral. Complementary function is nothing but natural response or source free response, and particular integral is called as steady state response or forced response. It is also called as complementary function is also called as transient response. First we will see particular integral, that means steady state response. In steady state, capacitor acts as open circuit. So capacitor will be open circuited. Since capacitor is open circuited, what is the value of I that will flow through the circuit? That is equal to 0. Now capacitor will also get charge up to the value of V, because there won't be any drop across resistor. So voltage across capacitor at t is equal to infinity is nothing but it will get charge up to the value of V. So what is the value of it? It is equal to 0. This is a particular integral solution. Now consider the case of complementary function. We know that di by dt plus I upon Rc is equal to 0. Now its solution is given as it is equal, for complementary function it is equal to a e to the power minus t upon Rc. What is a? A is nothing but it is a constant depending on initial conditions. So total solution it is equal to pi plus cf. Pi is nothing but 0, so we will get it is equal to a e to the power minus t upon Rc ampere. Now we will find out the value of a. A can be found out using initial conditions. So at t is equal to 0 plus, we can redraw the circuit as capacitor acts as short circuit at switching instant. So what is the value of I at t is equal to 0 plus? It is nothing but it is purely resistive circuit, so it is equal to V by R. So V by R at t is equal to 0 definitely is equal to a e to the power minus t upon Rc. Now t is equal to 0, so substitute t is equal to 0 at this point, at this place also. V by R is equal to a e to the power minus 0 upon Rc. That means we get a is equal to V by R. So what is the value of it that we get? V by R e to the power minus t upon Rc amperes. This is the value of current. Now we will find out the value of capacitor voltage is equal to 1 by C integral I t dt, integration from 0 to t, because we are applying voltage at t is equal to 0. That is equal to 1 by C integration 0 to t V by R e to the power minus t upon Rc dt. V by R is constant, take it outside. V by R integration of e to the power minus t by Rc is equal to minus 1 upon 1 by Rc e to the power minus t upon Rc in limit from 0 to t. So that is equal to 1 by Rc multiplied by V minus 1 upon 1 by Rc take outside, so it is minus Rc and e to the power minus t by Rc limit from 0 to t. That is equal to Rc will get cancelled, minus sign with V minus V e to the power minus t upon Rc minus e to the power 0. that is equal to minus V into e to the power minus t upon RC minus 1. Rearranging the same, we'll get V 1 minus e to the power minus t upon RC volts. This is the value of capacitor voltage for t greater than 0. Now we will see the case of source free RC circuit. Consider the case of source free RC circuit. Let's say at t is equal to 0, switch is moved from position 1 to 2. Now at t is equal to 0 minus, we will redraw the circuit. Since source was applied from minus infinity to 0, that means before moving switch from 1 to 2, circuit must have attained its steady state value because source was applied for a very long time, and in steady state we know that capacitor acts as open circuit. So current through the circuit will be 0 at t is equal to 0 minus, and there won't be any voltage drop across resistor, and complete voltage V will come across capacitor. That means Vc at 0 minus is equal to V, and we know from the property of capacitor that Vc at 0 plus is equal to Vc at 0 minus, that is equal to V. That means during this interval from minus infinity to 0, capacitor will get charged up to the value of V. Now for t greater than or equal to 0, we will redraw the circuit. Let's say this is R, this is C with initial voltage V. Let's say this node voltage is V1. This is Vc 0 minus, that is equal to Vc 0 plus, that is equal to V. Let's say this node voltage is V1. So let's say IC is current flowing through this, IR is the current flowing through resistor. Then using KCL we can write IR plus IC is equal to 0. But what is IR? IR is nothing but V1 upon R, and IC is nothing but equal to and IC is given as C dV1 by dt, that is equal to 0. Now rearranging the same, we can get V1 upon RC plus dV1 by dt, that is equal to 0, or dV1 upon V1 is equal to minus dt upon RC. Now integrate both sides, we get integration of dt from 0 to t, because switch is moved from position 1 to 2 at t is equal to 0, and V1 will be from initial value V, because initial value of capacitor is V, V to V1 t, right? Now dV1 upon V1 is nothing but equal to log to the base e of V1 from V to V1 t, that is equal to minus 1 upon RC t, right hand side will be. Now log to the base e of v1t minus log to the base e of v is equal to minus t upon rc, that is equal to log to the base e of v1t upon v is equal to minus t upon rc. Now we know that log to the base e of a is equal to b, then we can write a is equal to e to the power b, right? So rearranging the same, we get v1t upon v is equal to e to the power minus t upon rc. So what is v1t is equal to v e to the power minus t upon rc, right? What is v1t? v1t is nothing but equal to vct. So vct is equal to v e to the power minus t upon rc volts. That is the response of capacitor voltage when it is source free. Now at t is equal to or greater than 0, that means after moving switch from 1 to 2 there is no source in the circuit. That's why we are saying that it is source free RC circuit. Now in this case, what is the V? It is the initial voltage present on capacitor, hence we can also represent as V0. So in generalized form we write that VCT is equal to V0 e to the power minus t upon RC volts, and V0 is the initial voltage. Now we will see the complete solution when capacitor is present with initial voltage V0 and it attains some value, steady state value at t is equal to infinity. That means we are going to combine the two results of source free circuit and source circuit. In source circuit we know that VCT is equal to V1 minus e to the power minus t upon RC volts, whereas in source free circuit we have seen that VCT is equal to V0 e to the power minus t upon RC volts. Now when both the conditions are combined, we can write VCT is equal to V0 e to the power minus t upon RC plus V1 minus e to the power minus t upon RC. Now in this case, this is the response of source free circuit and this is source circuit response. In source free circuit, V0 is the VC at 0, that means initial condition, and in sourced circuit, what is V? That is the final value attained in the final value of capacitor voltage in the circuit, so that is given as VC of infinity. So rearranging the term, we get VC 0 e to the power minus t upon RC plus VC infinity minus VC infinity into e to the power minus t upon RC. Rearranging the same, we get VC at infinity plus VC 0 minus VC infinity e to the power minus t upon RC volts. Now this is the complete solution for VCT if circuit consists of capacitor with initial condition as well as it reaches some final value, that is VC infinity. Now in this equation, RC is called as time constant. RC is called as tau, that is time constant of the RC circuit. If it is charging case, then time constant is defined as the time taken by the voltage response to rise to 63.2% of the maximum value. Now we will see the case of sourced RL circuit. Let's say switch is closed at t is equal to 0. Now for t greater than 0, we can redraw the circuit as R L V. Now let's say IT is the current flowing through the circuit. Then using KVL we can write V minus IR minus L di by dt is equal to 0. We can rearrange the term and we get di upon dt plus R upon Li is equal to V upon L. V upon L. So this is the differential equation of first order. Now its solution is given as IT is equal to Pi plus complementary function. It is nothing but Pi, we have already said that particular integral, and complementary function is and CF is nothing but complementary function. Pi is also called as steady state value or forced response, whereas complementary function is called as natural response or transient response or source free response. Now we will see first the case of CF. CF is nothing but complementary function or source free. Since it is called as source free, V will be 0 in that case. So we can rewrite this equation as di by dt plus R upon Li is equal to 0. Now this is first order, standard first order differential equation, and its solution is given as IT is equal to A e to the power minus T upon L by R. Now this A constant depends on the initial conditions of the circuit. Now consider the case of Pi, particular integral, that means steady state response. We can redraw the circuit for steady state condition. We have already seen that inductor acts as short circuit in steady state. So what is the value of I in steady state? It is nothing but equal to V by R. So complete solution is given as CF plus Pi, that is equal to V upon R plus A e to the power minus T upon L by R. Now we will find out the value of A using initial conditions. Let's say at T is equal to 0 plus. We'll draw the circuit at T is equal to 0 plus. We know that inductor acts as open circuit at switching instant. So value of current will be 0 at T is equal to 0 plus. Substitute this condition in total solution. What is the value of IT we get? 0. That is equal to V by R plus A e to the power minus 0 upon L by R. That means A will be given as minus V upon R. So complete solution is V by R minus V by R e to the power minus T upon LR. That is equal to V by R into bracket 1 minus e to the power minus T upon L by R seconds. As we have seen in case of capacitor RC circuit, tau is the time constant, that is time constant of RC circuit given by R multiplied by C. Similarly, in case of RL circuit, tau is the time constant of RL circuit is given by L upon R seconds. So we can write IT is equal to V upon R into bracket 1 minus e to the power minus t upon tau ampere. This is also ampere. Now we'll see the case of source free RL circuit. Let's say switch is moved from position 1 to 2 at t is equal to 0. At t is equal to 0 minus since source has been applied from minus infinity to 0, that means for a very long time, circuit must have attained its steady state value, and in steady state inductor acts as short circuit. So inductor will act as short circuit, and what will be the current flowing through circuit at t is equal to 0 minus, that is I at 0 minus is equal to V upon R. That means inductor will get charge to value I0 from minus infinity to 0, where I0 is nothing but equal to V upon R. Now let's again draw this circuit for t greater than equal to 0. Inductor with initial current I0 present in the circuit, and voltage source V won't come into picture. Hence we said that it is source free RL circuit. Now let's say IT is the current flowing through circuit. So write down KVL for it. R into IT plus L di by dt is equal to 0, that is equal to minus di by dt is equal to R upon L of IT. Rearranging the terms, we get minus di by IT is equal to R upon L dt. Now integrate both sides. Dt is integrated from 0 to t, whereas I is integrated from I0 to IL of t. Right. Left hand side will be log to the base e I of t ranging from I0 to ILT with minus sign, that is equal to R upon L into t. Right hand side can also be written as t upon L by R, and we have already seen that L by R is nothing but time constant of the RL circuit. So we are going to write t upon tau. For left hand side, let's say take negative side on the right hand side, so it will be log to the base e of ILT minus log to the base e of I0, that is equal to log to the base e of ILT upon I0. We have already seen that log to the base e of A is equal to B, so we can write this as A is equal to e to the power B. Similarly, ILT upon I0 is equal to e to the power minus t upon tau, where tau is equal to L upon R. So what is the value of ILT that we get? ILT is equal to I0 e to the power minus t upon tau ampere, and tau is equal to L upon R in seconds. Now, as we have seen, ILT is equal to V upon R into bracket 1 minus e to the power minus t upon tau for sourced RL circuit, and ILT is equal to I0 into bracket e to the power minus t upon tau for source free RL circuit. Now combining the two equations, we get ILT is equal to V upon R 1 minus e to the power minus t upon tau plus I0 e to the power minus t upon tau. In case of sourced RL circuit, what is the V upon R value? It is nothing but IL infinity value, that means current in sourced RL circuit in steady state, and I0 is the IL at 0, that means initial value. So substituting these terms, we get IL infinity into 1 minus e to the power minus t upon tau plus IL0 e to the power minus t upon tau. Rearranging the terms, we get IL infinity plus IL0 minus IL infinity e to the power minus t upon tau ampere. This is the complete solution for RL circuit in which initial conditions is given as well as RL circuit attains steady state condition. RL circuit attains steady state condition at t is equal to infinity. Now based on the derivations that we have seen, we will see some gate numericals. Let's say gate 2011 numerical for EC branch, in which voltage source is given of 100 volt, R value is of 10 ohm, capacitance value is 50 microfarad, with given polarity it is storing 2.5 millicoulomb, initial condition given, and switch is closed at t is equal to 0. We have to find out ICT for t greater than 0. For t greater than 0, circuit will be something like this. Now, when for t greater than 0, direction of current will be top to bottom. So capacitor will get charge in this direction, that means positive to negative. But initial charge given is minus plus. Hence, when we are going to write equation for V is equal to Q upon C, in that case we have to take this sign as negative, because initial condition voltage will be negative. So that is equal to 2.5 into 10 to the power minus 3 upon 50 into 10 to the power minus 6, that is equal to minus 50 volt. So VC at 0 minus is equal to minus 50 volt, and because of the property of the capacitor, it does not allow sudden change in voltage. VC at 0 minus is equal to VC at 0 plus. Now we know that the equation of VCT is equal to VC infinity plus VC 0 minus VC infinity into e to the power minus t upon tau. What is tau? Is equal to RC, that is equal to 10 into 50 into 10 to the power minus 6 seconds. Now for t is equal to infinity, we need to find out VC at infinity. For t is equal to infinity, we will redraw the circuit, and it will be in steady state. It has attained, or it has stored the maximum capacity of charge it can store. So capacitor will act as open circuit in steady state, and there won't be any drop across resistance, since current passing through circuit will be 0 because capacitor is open circuited. So 100 volt will appear as it is across capacitor. So VC at infinity is equal to 100 volt. So write down these values: 100 plus minus 50 minus 100 e to the power minus t upon RC. That is equal to 100 minus 150 e to the power minus t upon 0.5 milli, right? That is equal to 100 minus 150 e to the power minus t into 2 into 10 to the power 3 volts. That is equation for VCT. And what is ICT? It is C dVc by dt. What is the value of C? That is 50 into 10 to the power minus 6. What is dVc by dt? dVc by dt 100, it is 0 because it's constant, minus 150 into e to the power minus t something, that is equal to, it will get outside, minus 2 into 10 to the power minus 3 into e to the power minus t into 2 into 10 to the power 3, sorry, it is plus 3 ampere. That is equal to 50 into 10 to the power minus 6 into bracket, this minus minus will get plus 150 multiplied by 2, that is equal to 300 into 10 to the power 3 e to the power minus t 2 into 10 to the power 3 ampere. Simplifying this, we will get 15 e to the power minus t 2 into 10 to the power 3 ampere. This is the value of ICT for t greater than 0. Now we will see another numerical from GATE 2002 electrical branch. Switch is closed at t is equal to 0. L value is 1 Henry, resistor value is 1 ohm, C1, VC2, this is 1 Henry and this is also 1 ohm. We have to find steady state voltages across C1 and C2. That means VC1 and VC2 at t is equal to infinity. We know that in steady state, capacitor acts as open circuit and inductor acts as short circuit. So at t is equal to infinity, we can redraw this circuit. Switch is closed. Inductor of 1 Henry will be short circuited. Resistor will be as it is. Another inductor of 1 Henry will be short circuited. Capacitor C1 will be open circuited. Resistor 1 ohm as it is. Another capacitor C2 will be open circuited, and this will be the complete circuit. Now let's say I is the current flowing through circuit at infinity. So we'll find out I infinity is equal to how much. Now C1 and C2 both are open, so for current flowing there is only one single path that is available, right? And writing down the KVL for the current loop, will get 10V is equal to I multiplied by 1 plus 1 ohm. That means I is equal to 10 divided by 2, that is equal to 5 ampere current will flow through the circuit at t is equal to infinity, that means in steady state condition. Now when 5 ampere is flowing through 1 ohm, there will be a 5 volt drop across this resistance of 1 ohm, and since this conductor is short circuited, there will be a drop of 0 volt across this inductor. Now voltage across C1 at infinity will be equal to same as that present across the inductor, that means it will be 0 volt, and in case of VC2 the same voltage will be as that of voltage across resistance, that is equal to 5 volt. That means Vc1 is equal to 0 volt and Vc2 is equal to 5 volt in steady state condition. Thank you.